Hello, my name is Taylor Balker, and this is Physics 2212 Lab 2 Lines of Charge. The purpose of this lab is to computationally model two charged tapes exerting forces on one another, assuming the tapes are lines of charges. We need to calculate the electric and gravitational forces on a line of charge, in this case a charged tape. Using the equations for electric field, gravitational force, and electric force, and also knowing that r is the position vector pointing from the source to the observed location, so r is equal to r observed minus r source, we will set up an experimental and a computational model to model the charged tapes. For our purposes, we are treating the tape on top as the system and everything else, including the bottom tape, as the surrounding. The result of doing it is the electric force and gravitational force both equaling 1.99339 times 10 to the negative 3 newtons in equal and opposite directions. First, let's look at our experimental model. Similarly to Lab 1, we set up the tapes as seen in the diagram on the right. Then, we calculate the mass of the tape, we measure the distance between the tapes, and we can use the free body diagram shown on the right to calculate the excess charge needed to float the tapes, which is 1.6 times 10 to the negative 9. Now we can set up a computational model using these numbers. Let's look at how I set up our computational model. Setting up the code is pretty simple because we can use some of our code from Lab 1. First, we establish the constants. They should all be the same from Lab 1 except for the charge, which we calculated using superposition and dE and dQ. Then, once we plug in that Q, we can find the electric field using the code that we used in Lab 1. Now we need to model the tapes as lines of charges. Here we create a line of point charge to take the electric field of each charge, and then we use dq and m, which are the total charge and mass of the tape, divided by the number of point charges in the line n. This gives us the partial charge and the partial mass at each point charge. Then we have to model the tape using this line charge function we created, and setting our vectors, our positions of each tape, so that they have the distance d, 0.0035, that we had calculated before. Finally, we can find the electric force and the gravitational force. Using a nested loop that runs through each charge dq and calculates the E field and electric force at each particle. Then by superposition, we can sum up all of the electric force acting on the top tape and model it in the middle of the tape. Then, the gravitational force is just the entire mass of the tape times gravity in the negative y-hat direction. Here we can see that after all of our calculation is done, we find that the electrical force, the gravitational force are equal, and they're roughly 1.99 times 10 to the negative 3 newtons. And we find that the necessary charge to float tape A is 1.75 times 10 to the negative 8. To get these calculations, we had to assume that we can ignore air resistance on a moving object or on the top tape, and that each U-tape we made had the same amount of charge evenly distributed along the length of the tape. Some of the limitations of this computational model is that we can't take into account air resistance, and we have to assume that the tape's widths are a singular point charge wide, but this is not true. And what if we modeled the charges as a singular point charge and then calculated Fe and Fg on that? Well, the electric force is not going to be entirely correct because we now have, in a line of charge, we have multiple charges which can act on each other that we have to add up, but in a case of a singular point charge, there's just one. And so to answer the why question, we know that the estimates of excess charge differs because we are modeling infinitesimally small pieces and summing them up. So we can say that Fe is going to be more accurate when we take a line of charge.